Hello and welcome to part 2 of the ARSET webinar, Satellite Remote Sensing for Agricultural Applications. My name is Sean McCartney and I'm a scientist at NASA's Goddard Space Flight Center. In part 2 of the webinar series, we'll be focusing on soil moisture for agricultural applications. In part 1 of the webinar series, we provided a history of Earth observations for agriculture. We highlighted satellites and sensors and their bio-geophysical applications for agriculture, as well as how to access these data products. We discussed the caveats and limitations of remote sensing and introduced the NASA Harvest Program. In today's webinar, we are focusing on soil moisture and NASA satellite observations and modeled products that provide critical information for drought monitoring, agricultural monitoring, and crop forecasting. Each webinar in this series will have a 1-hour presentation followed by a 30-minute question and answer session. The homework assignment for part 1 is already available on our webpage, and the final homework assignment will be available following part 3. Answers must be submitted via Google form with due dates of April 28th for the homework 1 and May 12th for homework 2. If you are interested in a certificate of completion for this webinar series, you must attend all the webinars and complete all homework assignments. You will receive a certificate approximately 2 months after the completion of the course from Marines Martin. The first half of today's webinar will focus on NASA's Soil Moisture Active Passive Mission, or SMAP. This will be led by Dr. Erica Podest, one of the ARSET leads for water resources and disasters. The second half of the webinar will focus on NASA's Land Data Assimilation System, or LDAS. This will be led by Dr. Amita Mehta, another ARSET lead for water resources and disasters. They will provide an overview, highlight examples for agricultural applications, and how to access the data products for soil moisture analysis. I will now turn the presentation over to Dr. Podest.
Good morning. I'm Dr. Erica Podest, and I'm a scientist at NASA's Jet Propulsion Laboratory in Pasadena, California. Today, I'll cover the first half of the webinar on soil moisture for agricultural applications, and I'll specifically talk about the Soil Moisture Active Passive Satellite Mission, also known as SMAP. So the outline of this presentation, I'll start out by talking about SMAP, giving you an overview. I'll talk about some examples of the use of SMAP for agricultural applications. I'll describe the SMAP products and finally how to access SMAP data. So let's get started with an overview of SMAP. So why measure soil moisture from space? The limitations in measuring soil moisture is that there are few ground stations around the world. And in addition, measurements at ground stations might not be representative of the surrounding landscape because they don't capture that heterogeneity. The advantage of measuring soil moisture from space is that these measurements can be done not only on a continuous basis and at global scales, but also because they're done applying the same methodology. And that's what SMAP does. SMAP provides frequent revisit global maps of soil moisture. Now, SMAP uses a microwave sensor called a radiometer, which operates in the L-band range, specifically at 1.41 gigahertz. The radiometer measures what's called brightness temperature, which is in kelvins, and from brightness temperature, soil moisture is derived as a product. The SMAP mission also had a radar sensor. However, that sensor ceased to function 3 months into the science phase of the mission. The reason microwave is used is because it is sensitive to soil moisture and also because it can image the surface of the earth regardless of daylight conditions or most weather conditions. Now, the sensor uses an antenna that is 6 meters in diameter. As you can see in this illustration, you can see the antenna. And this antenna, it actually rotates at about 14.6 revolutions per minute and creates a swath on the surface of the earth that's 1,000 kilometers wide. The orbit is a polar sun-synchronous orbit, and SMAP is at an altitude of 685 kilometers with a 6 a.m., 6 p.m. equatorial crossing. So that allows for a 2 to 3 day global revisit because of the swath-to-swath overlap. But in terms of an exact orbit revisit, it's an 8-day exact orbit revisit. SMAP was launched into space on January 31st, 2015. It took a couple of months for the satellite to be commissioned, and as of early April 2015, SMAP went into its science phase. So at that point, it started to continuously collect data. So here I've listed the characteristics of SMAP soil moisture measurements. The domain is global. The spatial resolution is at 9 and 36 kilometers. The temporal repeat is every 3 days. So every 3 days you have a complete map of global soil moisture. The sensing depth is approximately 5 centimeters. The measurement is volumetric soil moisture. That means that it's a measurement of the volume of water within a given volume of soil. And the accuracy is 0.04. So that means that 0.04 volumetric. So that means that there's the error is up to 4% volumetric. And the data access policy is the data is freely available. And I'll talk about where you can access the data at the end of this presentation. As mentioned, SMAP has a 3-day temporal repeat, and this is important because it captures that surface wetting and drying. And capturing the impacts of storm, interstorm sequences combined with the inertia of surface storage requires a revisit of approximately 3 days. And this figure shows these wetting and drying periods. The black line is continuous soil moisture over a month. The blue inverted triangles are soil moisture sampled every 7 days, and the red inverted triangles is soil moisture sampled every 2.5 days. And you can see that then sampling every 7 days misses those wetting and drying events, while sampling every 2.5 days captures those events much better. So soil moisture varies with space and time, and there are several factors that influence the amount of water in the soil. The primary driver of soil moisture is rainfall. Soil texture also influences how long water is retained in the soil. So for example, sandy soils are more porous and than silty soils, and hence sandy soils tend to hold less water than silty soils. Vegetation plays a role in soil moisture retention. We all know that a bare surface will dry quicker than soil under vegetation. And then finally, topography influences where water tends to accumulate, and you would expect flat surfaces to accumulate more water and for longer than steep surfaces. Also in the northern hemisphere, soils in south-facing slopes will tend to dry out quicker than soils in north-facing slopes. The reason SMAP has active and passive in its name is because of the type of sensors it uses. A passive instrument, a radiometer, measures the emitted radiation from a medium, from the surface of the Earth in this case. And it's the radiation that's emitted at 1.41 gigahertz. An active instrument like a radar is analogous to an ultrasound. So it provides its own illumination source and sends a wave and measures the reflection back from the target. As mentioned, the SMAP radar is no longer working, and SMAP has relied on its radiometer to produce soil moisture products. However, SMAP is using radar data from the European Space Agency's Sentinel-1 satellite, which has a radar sensor, and I'll talk about this a bit further along. The use of L-band in the micro range has certain advantages, as mentioned earlier. First, it's not significantly attenuated by clouds and rain, as opposed to visible and infrared images where clouds often mask the surface of the Earth. Also, second, we can see the surface of the Earth and make measurements day and night. Other advantages is that microwaves are sensitive to the water in the soil due to the dielectric properties of the soil, and these can change significantly between wet and dry soils. Also, L-band has a long wavelength, so it has a wavelength of approximately 24 centimeters. That means the distance from the peak of one wave to the peak of the next wave is 24 centimeters. And the longer the wavelength, the more it penetrates through the vegetation and into the soil. And so that's why SMAP can measure up to, in general, the top 5 centimeters of the soil. Higher frequencies or shorter wavelengths would not penetrate as deeply into the soil, and therefore the long wavelength at L-band is optimum for SMAP in terms of instrument design. So this is a basic overview of the measurement approach. The radiometer measures emissions and the radar measures backscatter from the land surface. So emissions that reach the radiometer come from the following components: the soil only, the vegetation only, and from the vegetation bouncing off the soil and back into the receiver. Now, interactions from the radar signal can come from the soil, the vegetation, and the vegetation soil or soil vegetation. The radar is more complex because the signal is transmitted and reflected, and hence these interactions with the vegetation can be complicated, and it's much more difficult to extract just the portion that pertains to soil moisture. So in order to measure soil moisture, you have to account for vegetation, you have to account for the surface roughness because that has an influence on the microwave signal, and you have to account for temperature, as well as a couple of other things, which I'll talk about in the next slide. So the SMAP soil moisture algorithm has a number of what's called ancillary data sources that inform the algorithm. So in order to tease out the soil moisture information from the signal, a large amount of information is needed about all the components contributing to the signal, such as vegetation, surface temperature, we talked about roughness. And so to do this, we bring in other data sets called ancillary data sets that can be used in the retrieval, and they provide information on different surface components. So for example, surface air meteorology, that contains information on air temperature, precipitation, vegetation opacity, so how thick is your vegetation, what's the water content of the vegetation, surface topography, for that a digital elevation model is used, soil textures, land-water boundaries, so we want to know where there's water and where there's land. Obviously, where there's water, a mask is applied so that there are no retrievals over areas where there's just water. Also, areas where there's permanent ice and snow, there are no retrievals over those areas, as well as over large urban areas. So in addition to SMAP, there are other soil moisture satellite products, and one of them is SMOS, which is from the European Space Agency. It has very similar characteristics to SMAP. It's an L-band radiometer with 40 kilometer spatial resolution, a temporal resolution of 3 days, and a sensing depth of approximately 5 centimeters. The difference between their soil moisture product and SMAP is that SMAP has what's called a radio frequency interference filter implemented, and this filter mitigates for noise in the signal, and as a result, the SMAP soil moisture data tends to be more continuous, so you don't have as much noise, especially in some parts of the world, in the data, in the product. There's also ASCAT, which is a European Space Agency scatterometer. It operates at a different frequency, but it still operates in the microwave range, so it operates at C-band, and there are products at 12.5 and 25 kilometers, and it's daily observations. So now I'll talk about some examples of agricultural applications where SMAP soil moisture data is being used. The United States Department of Agriculture uses SMAP to monitor global croplands and make commodity forecasts. And this is work developed with scientists at NASA Goddard, and they've used they've incorporated SMAP soil moisture data into Crop Explorer, which is a website hosted by the USDA Foreign Agricultural Service, and it reports on regional droughts, floods, and crop forecasts. Crop Explorer is a clearinghouse for global agricultural growing conditions such as soil moisture, temperature, precipitation, vegetation health, and more. The images here show that the average subsurface soil moisture anomalies average subsurface soil moisture anomalies over the southern portion of Africa for the 2016 and 2017 growing seasons. The negative values indicate that soil moisture conditions are below average, while the positive indicate a surplus of water. The area has been experiencing a decline in precipitation, reaching record low rainfall amounts, accompanied by high temperatures and evapotranspiration rates during the 2017 growing season. The South Africa 2017 drought caused about 29% decline in the region's wheat yield production relative to the previous year, according to the USDA FAS Crop Intelligence Report published on February 8, 2018. So that's the small insert located in the lower left part of the chart. And the current agency's crop growth and crop stress models are driven by soil moisture estimates that are generated using a simple hydrologic model. The model is highly susceptible to the quality of the precipitation data used to force the model. And so part of the study helps assess the utility of SMAP to improve the quality of USDA FAS soil moisture information and aid USDA FAS crop forecasting activities over poorly instrumented regions and areas that have poor precipitation data quality. So another application is SMAP for agricultural crop yield and food security applications. And the idea here is to use SMAP soil moisture to inform on crop yield and food security. And this is work that's been done by my colleague from JPL, Dr. Narendra Das. So the figure here shows yield in tons per hectare, and on the y-axis, and a year from 2002 through 2010 on the x-axis. So these are corn yields. And the red squares are actual observations of yields throughout these different years. The black circles are conventional crop modeled yield predictions, and then the green circles are yield forecasts with data assimilation in a data assimilation framework using SMAP, soil moisture as an input. And as you can see, in this case, when you use SMAP soil moisture in this data assimilation framework, it matches much better, or there's a much greater correlation when you use SMAP soil moisture to the actual yield observations than when you're just using a conventional crop yield model. So along these same lines, this example shows the relationship between crop yield and soil moisture. So agricultural models have been developed to predict the yield of various different types of crops at field and regional scales. And a key input into these models is soil moisture. This diagram relates the variation in regional average soil moisture to the variation in total crop yield. And you can then, you can see that they're nicely correlated. And you can take this, do this statistical analysis to develop probability distributions of crop yield based on soil moisture. So this example shows the improvement of drought and flood early warning with SMAP data. And this is work done by the Texas Water Development Board and UCLA. So this is the prediction of 2015 summer rainfall anomalies. And the colors here, the red indicates that it's below normal, green indicates near normal, and the blue indicates above normal. So these are millimeters per day. And what you're seeing on the far left are predictions using soil moisture as estimates from a model. The image in the middle are predictions using soil moisture from SMAP. And then the one on the right are the actual observed rainfall anomalies. So you can see that the predictions that used soil moisture from SMAP match the anomalies, the observed anomalies, much better than the predictions using soil moisture estimates from a model. In the next couple of charts, I'll talk about the SMAP products. So this is a list of the SMAP data products. NASA has a free data policy, and all of these data are freely available online. So NASA data comes at different levels, and let me explain what these levels are. The level 1 data is the instrument data, so that's the radar and the radiometer data, that's the raw data. The level 2 are the geophysical retrieval, so that includes soil moisture products, but they're on half orbit. So half orbit data refers to either the ascending or the descending data for any single day. And so for any single day, you've got ascending, you have about 16 ascending strips, as well as descending strips. The northernmost and the southernmost orbit locations demarcate the half orbit boundaries. The level 3 are global composites of the level 2 products for an entire day. So the daily composites are the ascending or descending paths for a single day gridded onto a global projection. And finally, the level 4 products are the modeled derived products. And in this case, they're model derived products of root zone soil moisture. So that is soil moisture at the 1 meter depth at the root zone level. So a model is used that determines or estimates what the soil moisture is 1 meter down. And there's also another level 4 product, which is carbon net ecosystem exchange. Okay, so one thing to note is that when the SMAP radar ceased to function, the SMAP mission decided to generate what's called these enhanced products. So these were products that were not originally planned by the mission, but in lieu of the circumstances, they were generated. So I've highlighted here with a red arrow, or I'm pointing with the red arrow, the soil moisture products that might be of interest to you when you're looking at what to download. Okay, so one of them is a SMAP radiometer and radar soil moisture product. The radar data that's being used here is from the European Space Agency Sentinel-1 radar satellite. That's the characteristics of this radar sensor are different from the SMAP radar sensor. And this SMAP team has used this data together with the SMAP radiometer to create a 3-kilometer soil moisture product. Then there's also an enhanced resolution or enhanced radiometer soil moisture product. So that means that the resolution of the radiometer has been enhanced. The radiometer soil moisture derived product is at 36-kilometer resolution. Now, the team has applied an interpolation technique based on Backus-Gilbert to enhance the resolution of the radiometer to 9-kilometer. And a soil moisture product has been generated just from the radiometer at 9-kilometer resolution. The other soil moisture product that might be of interest is the level 4 soil moisture product. So this has surface soil moisture and root zone soil moisture. And these are not really direct observations, but they're estimates using a model. So estimates of surface soil moisture and estimates of root zone soil moisture using a land surface model. This is an example of a level 3 radiometer derived soil moisture product. So this is gridded at 36 kilometers. And so this is a daily global composite. And to generate this composite, the processing software ingests 1 day's worth of level 2 soil moisture passive granules and creates individual global composites as these 2-dimensional arrays. So the composite, in this case, it used the descending passes. The descending passes are the 6 a.m. passes. And you ideally want to use descending passes because in the morning, the temperature of the soil tends to be in equilibrium with the rest of the land surface. In the afternoon, there might be differences, and so the algorithm may not be, the soil moisture retrieval algorithm may not be as accurate with the PM passes, which is around 6 p.m., as the ones in the morning. So the important thing to note about this and other level 3 products is that in the high latitudes, some of the SWATs overlap. And when they do, the data point with an acquisition time closest to 6 a.m. local solar time is selected. So this example shows the enhanced products, one of the enhanced products. So this one is the resolution of the radiometer being enhanced. And so the product on the left is a soil moisture product generated from the radiometer, the original radiometer resolution. And it's gridded to 36 kilometers. And the image on the right, it's the same area, same day. And so the resolution of the radiometer has been enhanced, and a soil moisture product has been created with this enhanced resolution. And it's been gridded at 9 kilometers. So you can see quite a bit more detail, obviously, in the enhanced resolution soil moisture product. This is an example of the SMAP enhanced active passive product using Sentinel-1, and this is work done by my colleague at JPL, Dr. Narendra Das. And so the image on the left is the SMAP, only the passive product, so the radiometer derived soil moisture, gridded at 36 kilometer resolution. And the image on the right is the same area using the SMAP radiometer data as well as Sentinel-1. So it's a passive active product, and this is soil moisture retrieved and gridded at 3 kilometer resolution. And this example shows surface and root zone soil moisture. So this is a level 4 product. Remember, a model was used to generate this product. All level 4 products are products that have been generated using a model. So what you're seeing here is root zone soil moisture. It's global root zone soil moisture from April 26, 2015. So this chart shows the areas where soil moisture is being retrieved. The areas in black are, it's the retrievable mask. And it follows the following specifications. So urban fraction is less than 1. So areas, soil moisture is retrieved in areas, in small urban areas, but in large urban areas where an urban area covers your entire pixel, those areas, there is no soil moisture retrieval. The algorithm just does not work in urban environments. It works in natural systems. Areas where water fraction, so if your pixel is less than half water, there's still a retrieval. There are quality flags to all of the retrievals indicating how confident the team is in that retrieval. And areas where there's a DM, so a digital elevation model slope, the standard deviation is less than 5 degrees. So even though soil moisture is being retrieved pretty much everywhere, it doesn't necessarily mean that the soil moisture retrieval meets the emissions accuracy requirements. So that's that 4% volumetric that I talked about in the very beginning. And this map shows the areas where soil moisture is expected to meet that accuracy requirement. So the areas in black are those areas. And these are areas where vegetation water content is less than 5 kilograms per meter square. So that means areas where the vegetation is not very dense. You can see that the Amazon and the Congo Basin, the accuracy there is not to mission accuracy requirements because vegetation there is quite dense and you have a large signal from the vegetation. So it's harder to really get to the moisture in the soil. Areas where the urban fraction is less than quarter of your pixel, areas where water fraction is less than 0.1 of your pixel, and the DM standard deviation is less than 3 degrees. So over these areas is where the mission feels confident that soil moisture meets the mission's accuracy requirements. So keep in mind that even though you might have a soil moisture value for the Amazon, for a pixel in the Amazon, it doesn't mean that that soil moisture value is necessarily accurate. So there are quality flags associated with each retrieval, and you can check for that accuracy. So this is a really cool animation of SMAP soil moisture, composited every 7 days from end of March of 2015 through this 2016. So it's about a 1-year video animation. And in land, the yellow means that the soil moisture is low, while the cyan and blue areas means that soil moisture is high or higher. And it's interesting, so you can see some interesting things here. In around June, July, you can see the onset of the monsoon season in India. It just suddenly starts and everything gets blue. You can see some flooding in Argentina around the summertime. You can also see some floods that occurred around 2015 in the Gulf states of the United States. Also to note is that the white areas are areas where there is no soil moisture retrieval. That's because these areas have snow. And so during the frozen part of the year, when these areas, the northern high latitudes, are covered by snow, there are no retrievals in these areas. Also, there are no retrievals like in areas over Greenland, areas that are permanently covered by either snow or ice. Another interesting thing to note is that the ocean, there's color there. Obviously, that's not soil moisture, that's sea surface salinity. So this is a product that has been derived from the data, from the SMAP data. It's not one of the nominal products from the SMAP mission, and it's been derived afterwards, after the fact. And that's a nice thing about having access to the raw data, is that you can derive other things of interest. So in this case, sea surface salinity has been derived, and areas that are dark blue indicate that salinity is lower, while areas that are yellow and red, the salinity is higher. And you can see some interesting things up in the northern high latitudes during the melt. In the spring, you have a lot of fresh water in these areas along the coast. Also, you can see the freshwater plume from the Amazon. So it's really quite interesting, this animation. So now let's talk about how to access the data. So before I jump into the websites where you can download SMAP data, let me just explain to you a little bit about the data product design. So all products are in HDF5 formats, and they contain not only the data parameters, soil moisture, but also all of the data that's used in the production of these primary parameters. So these are files that include metadata, geolocation information, quality flags, etc. The data are in east grid projection. That's an equal area projection. And finally, the values, as mentioned before, for soil moisture, they're volumetric. It's a volumetric measurement expressed as centimeter cube over centimeter cube. Most of the products are available from about April or July 2015 through present. The level 2 products, most of the level 2 products have a 24-hour latency, so that's 24 hours between when the observation was made and you being able to access it and download the product from the Data Archive Center. The level 3 products have a latency of about 50 hours from acquisition. The SMAP soil moisture products are archived at the National Snow and Ice Data Center. And if you follow this website, you'll go directly to the page where the data is hosted. So let's just jump over to the web page and I'll show you how to download the data. So here we are at the NSIDC SMAP page. And this is the main page that contains a description of SMAP and the instrument, the mission, etc. But some things to note here is on the left-hand side, there's a menu. And this menu has some tools, some interesting tools as well. So if you go to Tools, you can download tools to open HDF5 files. So if the current software that you're using does not open HDF5 files, again, you can use any of these tools. And these are all open source tools or even code. You can use it to open your file and then export that file into a format that your software can recognize. Okay, so let's go to SMAP data. And this will take us to a page that has a list of the different SMAP data sets. Now remember, we talked about the different level data sets, level 1, 2, 3, 4. So you have them right here. If you click on level 1, there's a whole list of data sets, the level 1 data sets that you can download. And there's a description to each data set. So there's the spatial resolution, the temporal coverage, and the parameters. So we're interested really in the level 2, level 3, level 4. So the level 2 data, you might be interested in the radar radiometer soil moisture product. So we talked about that. So it's using the SMAP radiometer and Sentinel-1 radar data. Okay, so that would be this data set here, SMAP/Sentinel-1. Okay, that's at 3-kilometer resolution. And that data set spans from 2015, so end of March 2015 through present. Now, in terms of level 3, you'll probably be most interested in the 9-kilometer soil moisture product. So we talked about different soil moisture products. There's the radiometer only derived soil moisture product that's at 36. It's gridded at 36 kilometers. And then there's the enhanced radiometer resolution soil moisture product, and that is gridded at 9 kilometers. Okay, and that data set starts from, again, same time frame, end of March 2015 through present. So let's click here. And this will take you to a page where I've already defined my area of interest. But basically what you can do in this page, let's clear this up. And I'll just show you what you can do in this page is you can filter the data sets. So you can set the time frame of interest. And in this case, I've set the time frame from the 1st of February of 2020 through the 5th of February 2020. So what you can do here is draw your area of interest, and let's just draw a small, no, I didn't want to do that. Just draw a small area there, and then the results will come back depending on the parameters that you set in your filter here. So the results are based on the filters that you set, and you do need to have an account in order to download the data. You can, the account is free, but you do need to set up this account. And usually you can set it up immediately, and you get access to, or you get, you can go into your account and download the data. So basically what you do is then you have, here you can order files, or it's a large custom order. So you order files, and you'll get an email providing you with a link where you can then download those images. Okay. Another way to download data is through the NASA Earth Data search engine. And so if you go to this link here, you'll go to this web page, and here you can do a search for SMAP. And you can also do set your filters, so you can define a start and end date. So let's start the 1st of February 2020, and let's just end, say, the 7th. Okay, and then you can define an area of interest. So let's just draw a rectangle over a small area of interest, in this case in Mali. Okay, so when you do a search for SMAP data, there are different products, SMAP-derived products, and the one we want to select is this one, the SMAP Enhanced Level 3 Radiometer Global Daily 9-kilometer Ease Grid Soil Moisture. So you select that, and there are seven granules, 7 images within your search area, or that cover your search area. And then what you do is you can, let's say we want to download all. Again, you also need to establish an account. Opening an account is free. So you download all. And the nice thing about this one is that you have an option to customize your download. So you need to input your email address, and you can specify what sort of output format you want. So if you don't want to deal with HDF5, maybe you prefer NetCDF or GeoTIFF or an ASCII file. So let's just go with GeoTIFF. It asks you if you want to subset. So remember, these are global mosaics. So you can enter a bounding box here for just your area of interest. Reprojection, do you want to reproject this? Remember, it's in on ease grid, and you can reproject it to these different projections. And then here, what you want to do is you want to select which files you want. So let's just open this. So within an HDF file, you'll have all of the files that were used to generate that particular soil moisture product. And if you're not interested in using or in all of that information, you can, in this case, just select the files that are of most interest to you. So you definitely want the soil moisture file. You might want the soil moisture error. You might want the latitude and longitude. So you'll have to go through all of these file names and select which one you're most interested in. Okay, in addition to the soil moisture. One thing to note is that there's the soil moisture retrieval data AM, that's the descending pass, and then there's the soil moisture retrieval PM, that's the ascending pass. You'll want to preferably use the AM. That's because the soil moisture retrievals with the AM pass tend to be a bit more accurate than the ones in the PM pass. Okay, so you're done, and then you download the data, and what the system will do is they'll send you an email, and they'll give you a link where you can download the data. Okay, so a final a platform that I wanted to make you aware of is called Appears. And this is actually my favorite platform. because you have many different options here for downloading the data. So you can, if you go to that link, you'll go to this main web page, and you can specify either point samples or area samples. So let's go with area samples, and we'll start a new request, and we'll just name this test SMAP. Okay, so then it says you can drop a vector file here containing your area of interest. So you have several options. You can either draw a polygon on the map delineating your area of interest, or just your point of interest, or just drop a vector file, a shape file here that will delineate your area of interest. And the file that's returned to you will be the values for the area that you've delineated. Okay. Again, you do here, you specify here there's a start date and the end date. And where it says select the layers to include, you'll say SMAP, and you'll have a list of the different SMAP products, and the one that would be probably the one you'd be most interested in is the SMAP Enhanced Resolution Radiometer Derived Soil Moisture product. So that's the 9-kilometer daily, global daily product. There's also the surface and root zone soil moisture that we had talked about. So if you're interested, probably not so much in the surface because this is a modeled parameter, but the root zone soil moisture. So these are both level 4 products. Then you can click here to select that product. So let's just select this, and then you'll have a list of all of the files that are included for each soil moisture file, right? So you want to select which one you're interested in. There's the retrieval quality flag, same as the Earth Data search engine. So let's just stick to soil moisture. Oh, you do use, okay. And then you have two options here, GeoTIFF or NetCDF, and then you can search for a projection. Here you have a number of different projections that were not available in the previous example that I showed you from the Earth Data search engine. So again, this is all a matter of preference, and then you click submit. Okay, so I didn't specify my area, but yeah, you go through the steps. You also need to have an account in order to download the data. Again, opening an account is free. Now, let me just show you very quickly how these data look. So I'm using Panoply, and I opened an HDF5 file. And when you open the HDF5 file, as I mentioned, each HDF5 file has all of the data sets, everything that was used to generate that soil moisture product. So you really have to search through the different folders. There's a lot of information in here. And what you want to do is you want to open the I have two different files here open. So you want to open the soil moisture retrieval data. Again, preferably you want to work with the AM rather than the PM. Slight differences between both of those, slightly more accurate in the AM. And then go through and look at all the different files that are associated with that AM retrieval. Obviously, the one that you're most interested in is the actual soil moisture file. So you click on this and create. And here we have a soil moisture file. And you can, in Panoply, you can play around with the scaling, the color bar, you can do overlays, and you can do a bunch of stuff. Okay, but the idea is if you want to export this, you can also export from Panoply into different formats. But so whenever you download an HDF5 file, it's, remember, and it's a level 3, it's a global image. So you will have to open the file and then extract your area or your point of interest. And that's why these other tools are quite useful. The Earth Data Search Engine or appears because you can actually extract the data for your specific area of interest rather than having to download an entire global file and then going in and extracting the values for just your area of interest. So that concludes this this part of the webinar. I'll be taking your questions at the end, and now my colleague, Dr. Amita Mehta, will cover the second part of this webinar. Thank you.
Okay, thank you, Sean and Erica, for the information about soil moisture from SMAP. Now, this section will focus on soil moisture for agricultural application from land data assimilation system. We already saw that remote sensing data about soil moisture from SMAP, high quality data are available since 2015. However, land data assimilation system, which is a modeling system, provides longer term estimation of soil moisture. And so this is also a source of soil moisture that we're going to look at. So what we're going to do is start with overview of land data assimilation system, then see a couple of examples of how LDAS is used for agricultural applications. Then we will have how to access LDAS data, and then we'll have a brief demonstration of how soil moisture from LDAS can give indication of agricultural productivity. So with that, we'll start with overview of land data assimilation system. First of all, why do we need LDAS? So basically that is for water and land management. And as you can see, there is a little schematic video here on the right hand side. But basically for proper characterization of spatial and temporal variations in water and energy states. That means soil moisture and temperature and fluxes. So energy fluxes like evaporation and runoff, they are critical for many applications. Weather prediction is one, agricultural forecasting, drought and flood risk assessment, improving understanding of land and atmosphere interactions, and then also climate change impacts. To understand all these, it's important or it's critical to know how water and land they interact with atmosphere and how water is cycled through different components of land and atmosphere. So that's why not only just for scientific understanding, but also for application, LDAS is needed. Another reason is if you look at surface-based observations as an example shown here on the right-hand side, these are soil moisture observations. As you can see, there are various ground and space-based land and hydrology observations, such as in this case, soil moisture. There are also precipitation, evapotranspiration, land surface temperature data are available, but they have spatial and temporal gaps. As you can see, most of the world is not covered by in situ data when it comes to soil moisture. Sometimes, even if the data are available, they're not really distributed to everyone to understand better. And so LDAS integrates surface-based, whatever is available, and remote sensing-based observations, and provides uniformly gridded, more frequent information than satellite can provide or in situ data can provide of water and energy components. And LDAS provides quantities that are not directly observed by satellites also. So in addition to soil moisture, which now is being measured by satellite, there is runoff and evapotranspiration, snow water equivalents. These are not directly observed by remote sensing, and they can be calculated by LDAS. So to get complete water budget and land atmosphere interaction through this cycling of water can be understood by running LDAS. So land surface model structure is shown here in general, and want to point out Dr. Matt Rotel from NASA. He is in charge of LDAS, and if any detailed questions, um, you can contact him for more questions. But so land surface models, they usually solve for interaction of energy, momentum, and mass between surface and the atmosphere. And in each model grid as shown here, usually the time step used is as short as 15 minutes. And not only like these are general grid, but subgrid level details are provided to have better interaction of surface, vegetation, and atmosphere transfer of energy and water. So precipitation and solar energy, they both are received by vegetation and surface, and how the water is cycled through different layers, how then it is given back to atmosphere through land and vegetation through evapotranspiration, that is calculated by LDAS. Also energy is used to for evaporation, evapotranspiration, and also to cycle water through the system. So these components are actually individually derived or calculated by LDAS. And for that, system of equations are used. So surface energy conservation equation, surface water conservation equation, soil water flow, and evaporation, which the well-known Feynman-Monteith equation. So these are the basis of LDAS. For LSM to run properly, there is forcing required. And so some input parameters first, these are static parameters, semi-static parameters, but they provide subgrid scale information such as vegetation greenness or leaf area index, vegetation classes, soil type, elevation. These have to be provided for proper characterization of water and energy transfer. And required forcing are basically weather parameters such as near surface wind speed uh, and precipitation, surface pressure, humidity and temperature, and energy, which is downward shortwave or solar radiation, and longwave radiation, which comes from the atmosphere itself. So all these are required inputs. And after going through the system of equations, then these are the outputs which are available from LDAS. Soil moisture, it's in multiple layers, as you can see, from top layer, top 10 centimeters, all the way to from 40 to 100 centimeters, and integrated 0 to surface to 100 centimeters also available. In addition, there are sensible and latent and ground heat fluxes, radiation, surface and subsurface runoff, soil temperature in each layer, snow water equivalent, snowfall and rainfall, evaporation, transpiration, and snow melt. These are available as outputs. We are going to focus on soil moisture for this particular session. There are a number of global and regional LDAS systems. Global Land Data Assimilation System, GLDAS, they are all linked here. You can get more information by clicking on them. North American Land Data Assimilation System, Famine Early Warning Systems Network or FuseNet Land Data Assimilation System, that's FLDAS, and the National Climate Assessment Land Data Assimilation System. As you can see, NLDAS and NCA-LDAS, they are regional, GLDAS and FLDAS are global. We're going to focus for data access and demonstration. We'll look at GLDAS and NLDAS, but you can find information on the same pages about these two also. So for GLDAS and NLDAS, a summary is given here, and papers describing these systems are provided here, references. One thing to notice is that there are multiple land surface models used in each of these systems. These are all different land atmosphere interaction models. So variable infiltration capacity, um, Sacramento Snow Model, Community Land Model, these are used by GLDAS and NLDAS. In addition, GLDAS has multiple versions. GLDAS 2 and 2.1, we're going to focus on 2.1, which is the latest version. And as you can see, this is one model that's used for 2.1, that's NOAA 3.3. Each of these have temporal information given here, hourly and 3 hourly. So hourly for NLDAS, 3 hourly for GLDAS, that information is available. In addition, daily and monthly data are also available. As you can see, NLDAS is available from 1979 onwards. GLDAS 2.1, which is completely forced by observations, is available from 2000 onwards. And resolution for NLDAS is 1/8 of a degree. For GLDAS 2.1 is 1/4 of a degree and 1 degree. These are the resolutions available. We'll focus on NLDAS and GLDAS version 2.1 when we look at data access. So what is the difference between GLDAS 2.1 and NLDAS or GLDAS 2.0 or other versions? It's basically where the inputs are coming from. For GLDAS 2.1, precipitation forcing is provided from Global Precipitation Climatology Project. This is based on multiple satellite and gauge data combined. Also, weather information comes from meteorological data from NCEP, which is National Center for Environmental Prediction, for their global data assimilation system. So atmospheric data also use remote sensing observations in assimilation and provide meteorological data, which are then given to GLDAS. And then surface radiation is received from Air Force Weather Agency. In NLDAS, precipitation is provided from Climate Prediction Center gauge data, also stage 2 Doppler radar. There is CMORPH, which also is precipitation information, CPC morphing technique, and North American Regional Reanalysis provides meteorological and radiation data. So these are various inputs, but they all provide outputs, which are integrated outputs, as we just saw here. These are the outputs available from each of the systems, no matter what the inputs are. Also, one more point to make is there is land information system. More information can be found here, and schematic is shown here. This is the software framework for LDAS. And what LIS allows is assimilation of different data sets into these land surface models, can allow different forcing for inputs, and it can be customized regionally. So LIS allows customized land data assimilation system. You can build, assemble, and reconfigure easily for any small region. So this is the software framework for LDAS. With that, we're going to see a couple of examples of how LDAS is used for agricultural application. FLDAS, or famine early warning, is shown here. It produces 10-kilometer resolution soil moisture estimates from 1982 to present, and it's updated twice a month. FuseNet was set up by USAID as leading provider of early warning and evidence-based analysis on food insecurity, and soil moisture is used for that in addition to other parameters from LDAS. It uses customized lists to leverage existing land surface models and generate ensemble of soil moisture, ET, and other variables based on multiple meteorological inputs or land surface models. So to reduce uncertainties, multiple inputs are used, multiple land surface models are used, and ensemble is then used to come up with parameters which can indicate if there is famine onset going on, or if there is food insecurity resulting because of that. And one example is shown here is the global soil moisture content shown here It shows these red areas where there is much less soil moisture, and that indicates where there would be less agricultural productivity. Another application is of NLDAS. Example shows its use for drought monitoring. And again, this is an example of soil moisture. This was in March 25th this year. As you can see, deficit of soil moisture in certain areas where one would expect drought or agricultural drought. And so NLDAS, this is an experimental drought monitoring. It's derived from near real-time soil moisture output from both the NASA MOSAIC and ANSEP NOAA land surface models in NLDAS. And the soil moisture anomalies and percentiles are derived from long-term climatological data from 80 to 2007. And more information can be found here. But basically, soil moisture anomalies and percentile values are used to predict or diagnose how drought, where it is occurring. One more regional project example is given here, and references provided here for details. It's ELDAS for Morocco. And this is again focusing just on the country of Morocco. It's the regional project financed by Global Environmental Facility, and it's managed by World Bank, USAID, and NASA. And that uses ELDAS to come up with a composite drought indicator, or CDI, which uses ELDAS output as part of it. And so as shown here, these are the maps of drought indices, and 2015-16, as drought was developing, it was monitored by using ELDAS on Morocco. So these are some of the examples which give you a deficit of soil moisture, how temperature is changing at land surface, and that provides you information about how agricultural productivity be affected by these parameters. So what we're going to see next is how to access ELDAS data. So we'll focus again on GLDAS 2.1 and NLDAS, how to get these data from these web tools. So first is Giovanni, and those of you who have taken ARSET webinars before are familiar with Giovanni perhaps. It allows you to pick a region, pick different analysis and different times. So spatial temporal subsetting is available, and you can have different analysis such as map, time series analysis. You can have vertical cross section, and histogram also are available. So we'll look at this, how to get data, how to get not only extract data, analyze it, have visualization done online without downloading data, and you can also download data using this. Then for bulk access of GLDAS and NLDAS data, we are going to look at this site called Earth Sciences Data Information Services Center, or GES DISC. This also allows spatial and temporal subsetting. Also, one can parameter subset parameters, also choose particular parameters such as soil moisture or ET, and one can then download data by using script or wget and curl, as we will see, to have bulk download in netcdf format so that you can do further analysis with it. So next we will have demonstration of data access. We'll focus on GLDAS 2.1, and we will also have an example of analysis of soil moisture as indicator of how it impacts agricultural production. Thank you.
So this is a demonstration of how to access and download ELDAS soil moisture data using Giovanni and GES DISC, the tools that we just reviewed. So now both these tools allow data search by a keyword. They both allow spatial and temporal subsetting of data and also downloading data in various formats. But GES DISC is more useful for bulk download of digital data, whereas Giovanni also allows online analysis and visualization before downloading the data. So we will see these features in this demonstration. So for this demonstration, we will focus on soil moisture data from GLDAS version 2.1 as an example. However, both GES-DISC and Giovanni provide access to NLDAS and FLDAS data also. Now, while GLDAS provides global soil moisture data, for the demonstration, we'll focus on a specific region. And for this demonstration, we've picked the country of Thailand in Mekong River Basin. This is a report by UN Food and Agricultural Organization, or FAO. And in their annual crop production report, what it's shown is that Thailand had crop production deficit in 2019 compared to previous 5 years and also compared to 2018. Now, there are several countries in the world where there was larger deficit, but we picked Thailand because overall in Mekong Basin, there was a drought-like condition. So what we will do is first look at GES-DISC and see how to download data for this region. And then we will see a case study of soil moisture analysis over Thailand using Giovanni. We will also see how soil moisture data downloaded from Giovanni can be readily used in software packages like Excel or QGIS to conduct further analysis. So with that, we will start with GES-DISC. This is the website. Here is the keyword search for the data that you want to download or looking for. So one point to note here is that you will require a login to NASA Earth Data. If you are not a user, when you will see a login button here, and when you click on that, it will guide you to register as a user. If you already are a user, you can use your username and password. This will also work with Giovanni. So all NASA websites usually require login with NASA Earth Data, and then the data are completely open and free. So with GES-DISC, we already know that we want to look at soil moisture from GLDAS version 2.1, and we are also going to look at NOAA LSM as we reviewed in the presentation. So we can search with the string. It looks through the catalog and comes up with the list of data available with GLDAS NOAA 2.1. So you can see that there are monthly data and there are 3 hourly data at 1 degree resolution and quarter degree resolution. Also, the temporal extent here is January 2000 to December 2019. You will also see in certain version there is more current data available. These are early products, but we're going to focus on these products which actually use GPCP as forcing. So we are going to look at monthly quarter degree GLDAS data. So once you pick that data, you can click here. It provides product summary here, data citation, papers, and documentation is given here as well about this data set. To access data for a specific region and download it, this subset and get data option is what we're going to use. Once you click on there, you can say refine date range. You can pick 1 year or many year. For example, we can pick 2019 January to December 2019 for temporal range. Then refine region. If you're looking for global data, you don't have to do anything, but if you are looking for a particular region, you can use to draw a rectangle or a circle or draw a marker. You can zoom in, you can pan the map. In this case, we're going to focus on the Mekong Basin, the country of Thailand, if you like. This allows to draw a rectangle, and whatever data you pick will be for this temporal range and this spatial domain. Here is also selection for variables. As we saw in the presentation, GLDAS has multiple outputs, and you can look through it if you are interested in more parameters, but we are going to focus on soil moisture 0 to 10 centimeters. You can pick that. This is surface soil moisture. You can pick other soil moisture levels, layers as well. And here are the units, kilograms per meter square. Once you pick that, you can go down to file format. There are multiple formats available. Either GeoTIFF or NetCDF is default. You can pick either one, and then you can say get data. Once you ask for data, it comes up with the list of files. These are files for 12 months of 2019. You can have them all the years, and so you will have all the files listed here. You can click on individual file to download on your computer, or you can go through this procedure shown here. You can download the link of all these files in a file, and then you can use wget and curl to download data. So if you have many months of data, you don't want to click individually, and then you can use this wget or curl. There is instruction for how to download wget or curl if you don't have them on your computer, also for your own operating system like Windows or Mac or Linux. But once you download, then here is the command to use. So wget, and here is the file name, url.txt, where you have saved all links to all the files that appeared on the previous page. And then it will go ahead and download each and every file automatically on your computer. So this is a quick way to download a large number of files, and that's why GSDisk is useful for bulk download. So next we will see how to analyze soil moisture data using Giovanni before we download the data. Here's the Giovanni website, and here also you will need to log in. Here's the keyword search window. We can be more specific here and say soil moisture GLDAS 2.1 and search. It comes up with the list of all the options. This is similar to what we saw in GSDisk, but specifically for soil moisture. Has 3 hourly as well as monthly data at 2 different resolutions between 2000 and 2019. We're going to pick monthly quarter degree soil moisture between 0 and 10 centimeters in kilograms per meter square, and then pick additional options. On top you will see analysis options. You can make maps of soil moisture. You can compare different data sets, take vertical cross-section. In this case, you will have to go down from surface to 2,200 centimeters. So it's different layers you can see, time series, and some other analysis options. We're going to do maps of soil moisture over Thailand and also time series of soil moisture over Thailand, focusing on 2019 eventually, where we saw that there was crop deficit. So let's pick time series first and go to seasonal option. Next, we can pick spatial domain. You can also draw a rectangle like in GSDisk, but in this case, we have shapefile selector. So different countries or river basin or US states can be selected by that shapefile, and in this case, we're going to pick Thailand, and this area gets highlighted. Next, we will look at temporal selection. First, we will look at annual cycle of soil moisture. So, for all months and for all years that data are available, let's see how soil moisture changes. So, start year is 2000 and end year is 2019. Once you select all these options and say plot data, the workflow launches and you will get the result in terms of time series. And I've already done this, so let's look at the time series. Here's the time series plot. What you see is from 2000 to 2019, each month how soil moisture varied, that is shown here. This is the soil moisture content. You can point the arrow on each of these curves and it tells you which month it is. You can also click down here to pick a particular month. So this gets, and it shows how soil moisture varied. Now this is a busy plot, but with all the months, you can see that in general, soil moisture for most months did decrease in 2019 compared to 2018. What we will do is we will further analyze this data using Excel to see this clearly. And for that, we can download these time series data. You can download each monthly file as netcdf, or you can download this CSV file, which you can further analyze in Excel. I have already saved this file on my computer that we will look at later. Before we do that, let's also do map analysis. So we can go back to data selection. And now we can do map. Here also, let's look at monthly and seasonal averages first. Here we can, instead of months, let's pick seasons. So we can quickly see seasonal maps of soil moisture over Thailand. And let's first pick 2000 to 2019. So we get a long-term mean of soil moisture over these seasons. Once you select all these options and plot data, you will get 4 maps, which I already have here. So these are long-term mean soil moisture map, 0 to 10 centimeter. On right-hand side, you will see the scale for soil moisture. And for 4 maps, so winter, spring, summer, and fall, all 4 seasons are shown here, long-term mean soil moisture, and it shows special variations over the country as well as temporal seasonal evolution of soil moisture. These data can also be further analyzed using QGIS or any other software after you download them. So once you pick this downloads options, you have these files as netcdf or as PNG images, as TIFF images, or as KMZ files, which you can view with Google Earth. TIFF files can be analyzed with QGIS or any other GIS. NetCDF files can be analyzed with other software or GIS also. So you can download whichever format is preferable. In this case, for example, I have downloaded June, July, and August of this long-term mean soil moisture in TIFF format, and I've already saved on the computer. Also, I've done one more analysis step. I have picked all 4 seasons, but just for 1 year now, 2019. And now when you plot the data, you get seasonal maps just for 1 year. So we have long-term mean as well as now we have a single year mean. So this is for winter of 2019, spring, summer, and fall seasons of 2019. And what we want to see is you can compare these maps with these long-term maps. You can visually look at this. You can also change color options here and set minimum and maximum values, same for all the maps, to compare them. So this is possible. So you can visually compare long-term mean with 2019 data and see whether you see excess or deficit of soil moisture also, which might indicate a reduction in crop production. But what we are going to do that, we're going to quickly see that in QGIS. So I have also downloaded this data as TIFF, and we'll just see now an example of how to further analyze this data in Excel and QGIS. So we'll start with Excel file. I saved CSV file of time series, and what you see here is all these years, 2000 to 2019, and all 12 months. Furthermore, I did average for each of these months, so January mean, February mean, and so forth, by using this average function here. And then I have made a plot of this long-term mean annual cycle, which is shown here. What you see is soil moisture is between May and October, there is maximum soil moisture, and especially in June, July, August, you have a lot of soil moisture, and that makes sense as this is the rainy season, and then soil moisture increases during that period. Next, what we've done is taken this 2019 soil moisture for each month and subtracted this mean data, mean soil moisture data from that, and so that this row here shows anomalies or departure from mean for 2019, and that is plotted here. So what you see here is that except for January and February, in 2019, all months had negative anomalies. That means deficit of soil moisture compared to long-term mean. So again, for crop production, soil moisture is not the only indicator. You will also look at precipitation, evapotranspiration, land surface temperature, etc. But in this case, clearly surface soil moisture or soil moisture between 0 and 10 centimeters from GLDAS does show an indication that, or it indicates that soil moisture anomaly indeed was negative, reflecting deficit of soil moisture and corresponds to, in this case, deficit of crop production. So this was more of like temporal analysis. You can also look at special part of it, and that I've done in QGIS, and this is a quick demonstration of that. So long-term mean and 2000 January, June, July, August, these summer seasons are loaded here, and then difference of 2019 minus this long-term mean is shown as anomalies here, and that was done just by using raster calculator and doing subtraction of these two layers. And this map shows anomalies or deviation, departure of soil moisture from long-term mean. And so corresponding to the time series, this shows the spatial part where, in which area there was soil moisture deficit in 2019 summer. This is summer, and you can see that all these regions, yellow to red, they all have soil moisture deficit in 2019. So just the conclusion of this demonstration is that GIS disk should be used for bulk download. It allows for file sort or files can be downloaded. In Giovanni, you don't have to download data to do calculations. You can do online calculations. You can do visualization and compare on Giovanni, or you can download those files and easily analyze in additional software such as GIS or Excel, as we saw here. So this concludes the demonstration, and I'll hand it back to Sean for question and answer. Thank you.
Okay, thank you, everyone. Now we will address the questions that you have. There is a question answer. You can type all your questions in the chat box, and then you will see this question answer document. We will also post this online. I have Dr. Erica Podest here, as well as Sean, and I myself will be answering some of the questions. So Erica, I invite you to take the first few questions which are related to SMAP.
Yes, of course. So let's start with question number 1. Could it be possible or reliable to retrieve soil moisture from SAR data with a high spatial resolution? Even though the SMAP soil moisture products are derived from the combination of passive and active microwave data, we've rarely seen the active-only soil moisture products, right? What's the future of the soil moisture retrieval study from SAR observations? These are really great questions. Okay, so I'll start with the first one. It is possible to retrieve soil moisture from SAR data only, and there are several algorithms out there in the published literature. However, it's not straightforward. Getting to soil moisture is with SAR data is not straightforward. I recommend for you to see some of the SAR webinars we've had in the past. We've had some advanced land cover SAR webinars where we talked about the use of SAR for agriculture and what the approach is and what some of the challenges are using radar. So radar is an active sensor. So it sends a signal. That signal scatters when it reaches the surface of the earth. And then part of that scattered energy is collected by the sensor. And so that signal interacts with different components of the land surface as it goes in and as it is reflected back. So basically, you need to be able to characterize the other components of the land surface. In your signal, you've got information about vegetation, roughness, water content in the vegetation. You've got a whole bunch of information within the SAR signal. And so basically, you have to tease out the land cover component to get to the part that corresponds to soil moisture. So the SMAP soil moisture products are derived primarily from microwave data. Initially, there was the radar, which ceased to function early on in the mission. And so SMAP has been relying primarily on its radiometer, which is passive. I did talk about a SMAP product that uses Sentinel-1 data, and that's C-band data. So you can download this data and test it. It is a beta version. So, but you can certainly have access it without any cost. So I hope that answered your question about why we rarely see the active-only soil moisture products, just because it is more challenging. And what is the future of soil moisture retrieval study from SAR observations? So there will be a radar mission called NISAR in the next coming 2 years. And it's a joint mission between NASA and the Indian Space Agency, Israel. And that has an L-band SAR sensor. And I think there will be, or that data can be used to try to get to soil moisture. And it is ideal, it is an ideal frequency because L-band penetrates deeper into the soil. So it's better to get at soil moisture. Question 2, can I perform wheat crop mapping using Sentinel-1? And yes, you can. I'm not sure what you mean about wheat crop mapping. Are you trying to identify wheat crops, or are you trying to identify the growth stages in wheat crops? So I suggest going back to the SAR webinars that we did last year. And there's a couple of webinars on agriculture, and those were led by Dr. Heather McNairn from Agriculture and Agri-Food Canada, and she did an excellent job in showing how you can use SAR for agriculture. What free computing tools are available for digital processing of satellite images by remote sensing applied to surveying land cover? So there are a number, and as listed here, there's a Google Earth Engine, there's SNAP, which is ESA, the European Space Agency's software to not only process and analyze Sentinel data, but it allows you to process and analyze other data as well. There's QGIS, Python, R. Question number 4, if it's sun synchronous, why do we need active sensors in SMAP? I'm not quite sure I understand that question. So it's sun synchronous, it's actually going over the equator at around 6 a.m. And 6 p.m. And so when you're using SMAP-derived products, you'll see that there's a soil moisture product that is derived from the morning pass, the 6 a.m. pass, and another one that's derived from the evening pass. And the one that you want to use is the morning pass. And the reason for this is because the radiometer is sensitive to the temperature. And in the morning, everything is it's assumed that everything is in equilibrium. In the afternoon, you have more changes in temperature, so the vegetation is going to have a different temperature than the soil. And so the soil moisture retrieval will be a little different and not as accurate as the morning retrieval. Question number 5. I'm building a model for crop water requirements, which gives daily outputs to farmers about their crop water requirements, soil moisture, ET, etc. Which free and commercial items do you advise which give daily satellite images with appropriate resolutions? Okay.
So
Daily, so I'll talk about SMAP. SMAP is not daily, so SMAP has daily observations, but it really covers the globe about every 3 days. If you're in the northern high latitudes, maybe every 2 days because there's a bit more overlap. Amita, would you like to talk about the other products?
yes, so LDAS provides not only daily, you can go 3 hourly as well. It's a model data, so it integrates satellite and in situ data and comes up with uniformly gridded frequent data. So daily data, as we saw, can be opted from LDAS. We focused on monthly data, but you can get daily data. So both soil moisture and ET are available from LDAS. Resolution, of course, is quarter degree in this case, so it's not super high, but we will see in the last session that there are high resolution ET data available based on MODIS, Landsat, and now even WIRS sensors. So we will have an overview of that in week 4. These are all free data. I'm not sure, or I'm not familiar with any commercial data which are available. So ET data from MODIS also has, they're semi-daily, 1 to 2 days. Landsat data are every 16 days. So these are not daily data, but so that way LDAS provides you moderate resolution or quarter degree data at almost daily. So you can combine different data sets as well from satellite and model to build your model.
Great. So the next question, what is the extension of the data of SMAP? I'm not sure I understand that question fully in terms of extension of the data. So there's been an enhanced products that are derived, and those products have been derived from the beginning of the mission. So if you go to the NSIDC, to that page I showed you, it shows you the coverage of data. So SMAP was launched in early 2015, and the science phase of the mission started around early April. So there's SMAP data that goes from early April 2015 through present. SMAP soil moisture data. Question 7, how will the soil moisture be applicable for the agricultural dominated Gangetic Plain of India? I think what soil moisture allows is to see the dynamic variability of soil moisture in this large area. Amita, would you like to add anything to that?
Yes, so basically if you can monitor changes in soil moisture throughout the growing season, that will help you assess water availability for crops. So that is one way of looking at it, because of course precipitation, land surface temperature, ET, they all matter, but both soil moisture and ET, they indicate hydrological deficit of water or hydrological drought type of conditions. So just monitoring soil moisture over the plain would tell you which part has water deficit and which part are okay. So I guess just throughout the growing season, monitoring soil moisture does indicate availability of water for crops. That's my conjecture.
Okay, question number 8. How is SMAP different from wetness index in tasseled cap transformation? So I have not done a comparison between the two to tell you how it's different, but tassel cap transformation, you're using optical spectral data. SMAP is using microwave data. So there is a fundamental difference there in that with microwave data, you have the ability to penetrate through certain level of vegetation and into the soil. And that's something that you cannot do with optical data. Question 9. Is there any open source code available for crop type mapping? Amita?
Yes, I think, Sean, you may add more to this, but there is open source code available through this site here for crop type mapping. And Sean, please add if you want to add any information to this.
Yeah, there's a list of different open source code you can find going to this link. One caveat being a lot of the research is empirical in nature, so it will be applicable to that specific study area. So you will need to be careful when you're going through the different code, which can be found on that link. I think that's one of the challenges is finding robust code that is applicable to wide geographies in different continents. But yeah, definitely go there and you can search for a code.
Okay, so question number 10. Over what period is the SMAP soil moisture anomaly calculated? So SMAP has a number of products that you can access that are freely available. There is no such thing as a SMAP soil moisture anomaly. You can calculate that yourself. And the period of time that SMAP has a soil moisture product starts, as I mentioned, from April 2015 through present.
So question 11 is how is root mean square error calculated? And I'm not sure whether you're asking about any specific data set here or general how it's calculated. So usually, I mean, there are standard routines to calculate root mean square error. It takes data that you want to compare with in situ data, take the difference, square them, add them over the period or the domain you are interested in, and then just normalize with the number of data points that you have. So that's just the procedure. But basically, it just tells you, it helps you compare your satellite data or model data with in situ data and see how different they are and what kind of errors they have. That's what they mean. I'm not sure whether you're asking in general or you have any specific parameter in mind, but it's a standard way of looking at error estimates.
Okay, question number 12. Despite the spatial resolution of SMAP is approximately 9 to 40 kilometers, would it be viable to perform small-scale soil moisture analysis, 10 meters to 500 meters, by conducting calibrations using SMAP values as a reference? Yeah, I have to think about this. I mean, this is sort of a scaling exercise where you're looking at the variability within a SMAP pixel, within a SMAP soil moisture pixel.
So I think it
So
would matter a lot on soil characteristics plus what kind of slopes within that pixels are. So I guess if you have in situ measurements which are higher resolution over some region, I don't think you can downscale without having soil characteristics information and slope information at that resolution. Like 10 meters, you need to know what kind of soil is there, how much will percolate, how much will stay, and if you know the slope, how much will run off. So that would help you decide how to distribute a SMAP pixel into high resolution. This is what's done with precipitation also, but downscaling usually is a tricky issue. One has to be careful.
good point. Yes, definitely. That would be the approach for this.
So question 13 is about the pest problem, and obviously moisture matters, also temperature also matter. I'm not aware of any technique or model at this point which can say anything about pest problem or can address that. Sean, if you have anything, otherwise we can come back and answer this question once we have some information.
So question number 14, can a radiometer resolution be brought down under 5 kilometers? Any insights into future missions providing improved resolution with a passive microwave sounder? So you can enhance the resolution up to a certain point. Actually, the SMAP radiometer, the original resolution is around 40 kilometers and it's gridded to 36. The enhanced resolution is actually around 25 kilometers, but it's gridded to 9 kilometers. Insights into future missions providing improved resolution with passive microwave. I don't have any insights into upcoming missions.
No, I don't know about that high resolution, but if you look at something like GMI, so GPM microwave imager, for certain frequencies, it's a passive instrument. It has resolution of about 5 to 10 kilometers right now. but I'm not aware of any sounder or future passive microwave sounder with that resolution.
Question 15, was this SMAP 9-kilometer data downscaled from the 36-kilometer product? What are the potential errors associated with the interpolation? Yes, so the SMAP 9-kilometer was through an interpolation technique. The resolution was enhanced from 36 and it's gridded to 9 kilometers. What are the potential errors associated with the interpolation? If you send me an email, I can point you to the technique and some of the errors associated with interpolating. The next question, 16, which SMAP data is used by USDA for crop forecasting activities? I believe USDA is using the SMAP level 3 soil moisture data, the 9-kilometer, but I would have to double check on that. Question 17, would it be possible, useful to merge the SMAP with the ARSET 2 soil moisture? Yes, absolutely. Especially if there are gaps, SMAP, the data tends to be filtered wherever there is radio frequency interference. ARSET 2 is a different frequency, so you will be seeing soil moisture at a different depth, actually. So it's much shallower than SMAP. How does the algorithm work in urban areas? Does it use any proxy or just show pixels with no values? So for SMAP, the algorithm does not work in large urban areas. The algorithm is meant to work in natural systems, and urban areas, it just gets very complicated with all of the paved areas. So basically, large urban areas are masked out.
Question 19 is brightness temperature different from LST? Yes, they both are different. LST is land surface temperature, and brightness temperature is usually derived from top of atmosphere radiance measurements. So when you have any radiation that's going to space, that's converted back to equivalent temperature of the surface atmosphere system. That's how generally it's defined. So brightness temperature does not directly reflect LST. No. Can we use the KML file for the boundaries of the data which is to be downloaded? If you're talking about GES disk or Giovanni, I think once you download data, you can use KML file, but I'm not aware of ability to upload KML file. There on Earth data, I think there is a way you can upload your shapefile, Esri shapefile, to select your domain. And I think Appears also allows you to upload your upload a shapefile to sort the boundaries.
Does NSIDC require a separate account than NASA Earth data? So NSIDC is part of NASA's Distributed Archive Center. And so you can use the same Earth data account to access all DACs. Question 22, are any of the SMAP products delivered as geotiffs? Yes. Through the Earth data website, you can opt to download the data as geotiffs. And Appears also allows you to download the data as geotiffs.
Question 23, can we use the softwares given on the site to read the HDF files for reading other HDF files rather than using it for only SMAP products? Yes, absolutely. The software will read any HDF file, not just SMAP HDF. Question 24, is it possible to access the SMAP datasets using an API? Yes, it is, and if you follow the link below, it indicates how to do that. Question 25, can we use SMAP for delineation of groundwater? That's an interesting question. So SMAP is looking at the top 5 centimeters of the soil. So you're just looking at surface water. You're not getting into groundwater. There's other data sets. There's a satellite called GRACE, which does get at indirectly at assessing groundwater change, actually. Can extract values to points be generated on the net CDF format of the SMAP datasets? Can the points extracted be taken as soil moisture values? I believe you can, yes. Question 27. What size of a farming operation would benefit from using these satellite data? And how are they using it? It seems to us the resolution and capabilities to cover very large areas and probably used for more regional analysis. What are the panelists' thoughts on this? Yeah, that's a really good question. I mean, obviously, SMAP has a 9-kilometer resolution, so a moisture product. And so if you're looking at small farms, you're not really characterizing small plots or small farms. So it's really more for larger agricultural fields, especially in industrialized countries. You have larger fields and for regional analysis. But Amita, perhaps you want to talk about the products, the other products.
Yes. No, you're right, actually. These products, because of the resolutions, that's the limitation, that you can look at regional variations only, not very small scale or variations or farm scale. But you can use these data as input to either crop models or watershed models for looking at high resolution modeling. These data can work as forcing for that or boundary conditions for that. That's possible.
Okay, the next question. Oh, Amita, perhaps you can take that one, question 28.
Yeah. So how does the accuracy of LDAS vary over different land covers? We will we'll put some references here for you to look at when we complete this question answer sheet. But yes, it does vary with land cover, but I'm not sure whether it's easier to quantify over grassland. I will have to come back and answer this question once I have looked at the correct answer, because I think it has been validated for different land covers in different parts of the world also. So I haven't seen it mentioned somewhere that it's easier to quantify over grassland. Yes, comparing the resolution, considering the resolution of the model, it seems reasonable that you have uniform land cover, performance would be better. Accuracy would be better than varying vegetation cover, or if you have forests or woods which are sub-grid scale, smaller region that are not represented. So I will have to go back and find some references for this. So we will.
How accurate?
Yeah, go ahead.
Apologies.
So also, Erica, I think we're just about noon now. So you can take the next couple of questions about SMAP, and then what we will do is go through all the questions, remaining questions, and answer them online. And this document will be available from ARSET website, so you can go back and read the answers.
Great. So I'll quickly go through the SMAP ones. How accurate is the SMAP time series for one pixel or a group of pixels? Would the accuracy and accuracy be relatively stable at each location? Yeah, so SMAP has a whole calibration validation effort to make sure that if there are any biases in the instrument in time, those are corrected for. So it should be pretty consistent. Now, the accuracy for a single pixel is going to vary on the land cover for that pixel and how that land cover is changing. So every pixel value, every soil moisture value has an accuracy associated with it. So even though there might be a retrieval, the accuracy might not meet the mission accuracy requirements. I hope that's clear. So the mission accuracy requirement is up to 4% error volumetric, okay? So in some areas, it's not going to meet that because the vegetation is too dense, the water content in the vegetation is too high, and that signal can't really get through the vegetation and detect the soil moisture in the soil. Question 30, how does the instrument differentiate the depth of surface and root zone? So root zone, it's actually using a model. So that's a level 4 product that uses a model that takes the moisture at the surface from the observations, and then through infiltration, through texture, land cover, a number of different ancillary parameters, determines what the moisture is at the root zone level, which is 1 meter down. Okay, so as far as I'm seeing, those are the ones directly related to SMAP.
SMAP. Just a couple of more questions we can quickly look at. Question 32 is about, is LIS publicly available for free? Yes, it is. In the presentation, you will see the link to LIS, and we'll also post it here. You can customize it for your own region, so software is available. Do you know of higher resolution model that is located in the tropics? So as far as NASA models are concerned, these are the models. High resolution model, highest resolution available is 1/4 degree, even in tropics. Could SMAP data as well as LDAT products be used for irrigation scheduling or groundwater recharge for a specific area? Should be possible for irrigation scheduling over considerably large region. You can, because say LDAS is 25 kilometers and SMAP varies from 9 to 40 kilometers. So maybe about that scale you can use it for irrigation scheduling. We will see in session 4 that ET is available, and that actually is used for monitoring irrigation scheduling or scheduling when to actually irrigate. So it should be possible. For groundwater recharge also same thing. I guess depending on the resolution, you can use that. Does Giovanni allow you to download large amount of data through scripts? I think for large download of data, you would use GES disk. There is a way to do the same thing if you, but you still have to have the list of files that you got from Giovanni. They have lineage of which files are used, and based on that, it should be possible, but the easiest thing is to just use GES disk. Are all these products available in Google Earth Engine? Not all of them. No, I'm not sure about SMAP. I don't think LDAS is available.
Yeah, SMAP, there is a version of SMAP. It's at a 1/4 degree spatial resolution, and it's been combined with, they're using a ensemble common filter data simulation approach. So if you want the original soil moisture product, you have to go to some of the websites that I showed you.
The instruction to download using wget for Windows OS does not download all files and timeout after a few files. Can you post the bulk download that works? Okay, we will have to revisit this question. I will check on that because since I do not use Windows, I have not encountered this. So we will get back to you on that. Another question, what Python libraries are generally recommended for use by consumers of data in netcdf or HDF formats? I'm not aware of any specific, I'm not familiar with exact which libraries. The version that personally I use is the Anaconda Python, and that comes with these libraries. So we'll get back to you on that. How can we use FLDAS for food security? So you can see the example, this famine early warning network, it uses FLDAS, and you will also see the link to FLDAS in the webinar, in the presentation. You can go through that, how it is used for food security. So basically it's for a famine early warning. So that it allows you to plan if you have to get food from somewhere else. Then what does unit of soil moisture kilograms per meter square mean? So this is in the LDAS. It is amount of, so mass of soil moisture in unit area, that's what it means. Will you cover shallow groundwater from LDAS assimilation? Not in this webinar, we're not going to cover that, but we are planning a more advanced webinar in near future where you will calculate water budget, and in that we will talk about shallow groundwater. How can we compare the ARSET soil moisture with in situ data? So you will start with remote sensing soil moisture such as from SMAP, extract data at a particular latitude longitude grid which has in situ data location within that grid, and then you will just use, ideally you will do this for some period, some time, and look at time series, and then any software can help you compare, so take bias or errors between the two. So we will go back and revisit some of the questions and post the question answer sheet on this document on the website. So we ask you to please refer to that later on. And next week, we're going to have presentation by Sean McCartney about, again, using some of these for crop mapping. And so we hope to see you next week. Thank you so very much. So on behalf of the ARSET team, we thank you all for attending this webinar. We'll see you next week.